Alright guys, welcome to our last lesson for Unit 2. Next class we'll do a little bit of review for our test. But yeah, this is it for Unit 2. So we're going to continue our discussion on slope fields today. Last time, I think it might be good to kind of start off with a little bit of review of what we learned last time. Last time we talked about what a slope field is. And what is a slope field? Well, if you have a function and you find its derivative, then you have what's called a differential equation. And then if you just plug in as many values of x and maybe y as is needed, you can sketch the slope at a bunch of different points and end up with what's known as a slope field. And then we learned some tricks on how you can match a slope field to its differential equations. So in other words, I gave you guys a bunch of slope fields and a bunch of differential equations. And based on the equations and the slope fields, you should be able to match which one goes with which, right? Well, today we're going to focus not on the differential equation, but we're going to focus on the original function, the particular solution, in other words. So, in other words, last time we were dealing primarily with matching the graph to f prime. But today we're going to be matching the graph to the original function f. So we're going to learn how, I'm going to give you a slope field, and your job is going to be to match the slope field to a particular solution, or the original function itself. After that, we're actually going to learn how to sketch a particular solution as well. Alright, let's go ahead and continue on here. So the first thing I want to do in our lesson today is I would like to start by looking at a graph. So let's consider the following function. Y equals x to the power of 3. So I just want you guys to look at that graph and recognize what it looks like. Okay? Now the next thing I want us to do is I would like us to find the derivative of that function. And so here's the derivative of that. Now, I'm going to go to a different website other than Desmos here, and I'm going to go to something called Geogebra because it has a really cool thing called a slope field plotter. So you guys remember what we learned last time, how to sketch our slope fields and how tedious that was? Well, this is a nice little website that'll actually just do it for you. It's called Geogebra Slope Field Plotter. But anyway, so now remember, whenever you do a slope field, you're not graphing the original function. So I'm not going to graph y equals x cubed. Instead, I'm going to graph the differential equation, the derivative of that, which is 3x squared. And I want to sketch a slope field using that slope field, so or that differential equation. So I'm going to put 3x to the power of 2. Enter. And there's the slope field. Wow, it just did it for us. What's really cool about this is you can affect the density. In other words, how many slopes you get. So you can make it really sparse, or you can make it really heavy. And also you can affect the length of your slope lines. You can make them really basically like dots, or you can make them really long to where they almost connect. I like them right in the middle myself. And so there's our slope field. Okay. Now, I want you guys to notice something though. If you imagine these slope fields here, like they are, like imagine this picture is like a picture of a river, okay? And imagine these little lines that we're looking at are like the current of the river. And so you can kind of imagine that if you were to, like, let's say start like right here, and if you followed the current, you're going to go up, and then you're going to follow that current. You're just going to keep bending up like that. Now what's interesting about that is that matches the picture for the original function that we had earlier. Right? That's the graph of x cubed. Here is the slope field of all the slopes given by 3x squared. And when you put them together, you kind of can see the shape of that cubic function coming out of it. Now here's another cool thing this website does. I can click this little button here and it puts a dot And wherever that dot is, that gives you a general solution. As you guys can see, this green line follows the current of the river there. The slope field basically tells you what direction they're going. So what I've heard this likened to is a river where, like, the dot represents a stick that you drop in the river or a feather or something. And once you drop it here, it's just going to follow the path of the slopes, and it's going to trace out that line. Okay? And so as you guys can see, last time we learned how to sketch slope fields, and then we learned a lot of different ways you can match a slope field to its differential equation. But you can also match a slope field to its particular solution. Because if you know that x cubed graphs look like that, which they do all the time, then you could just look at this graph and know, oh, well, this must be a slope field for that. So what am I getting at? Let me show you what I mean. Your student practice for today is you have all these slope fields, and you have to match each one of these, not with the differential equation, but with an original function. And so the first thing you're going to do is you're going to sketch what a particular solution might look like, and then based on that particular solution, you're going to pick which equation that goes with. Like, for instance, if we sketched a line in here, which one of these would look like a parabola? Because that would be this one right here, because that's a quadratic. So you do need to know what each of these graphs typically look like in order to do that, though. So it does require some pre-calculus skills, but I'll share that with you before we get started. But before we do that, here's what I want you guys to do. Is I'm going to put a dot somewhere on this slope field. I'm going to put a dot like right here. And I want you guys to see if you can sketch a line that would go through that dot and follow the slope field. So once again, imagine this is like a river. And this dot that I just put here, imagine that's like a feather that I put in the river. And it's going to float along the slope field. So see if you guys could sketch what that would look like. You know, you could do it mentally. You could just trace it with your finger on your computer screen, whatever you want to do. Now, I'm going to take this one point they gave us here, and I'm going to slide it up here. And that's what your graph should look like. Let's do another one. What if I dropped the feather or the stick in the river, like maybe right here? What would that look like? Well, as you guys can see, if we're going to the right, it's going to shoot up really fast because the current starts going really straight after that. But as we go to the left, it's going to flow sideways, and then it's going to get flat, and then it's going to shoot down after that. So see if you can sketch what that line might look like. Just trace the path of the current starting from this point and see if you can figure out what it would look like. All right, so I'm going to put it up there now. And here's my dot. I'm going to move it right to where I wanted it, and that's what it would look like. So sure enough, like we said, as we go to the right, it just shoots straight up. But as we go to the left, following the current, it goes down really fast at first, but then it starts to bend. So I started bending a little early up here, I guess. But it starts to bend as it goes down here, and then it starts to shoot back down. Right there. All right? So that's the idea there. Now, let me give you guys another one here. But this time I'm just gonna change the function completely. I'm gonna make it a different differential equation. Let's go ahead and do like 2x minus y to the power of 2. Let's see what that looks like. That might be really weird. Let's get rid of that. And now I'm gonna drop a stick in the ocean or a stick in the river. Here we go. I'm putting the stick right here. I want you guys to see if you could trace the path and see if you can figure out what that would look like. So if I were to put the stick here, obviously it's going to start shooting up, right? I'm not going to get this traced really well, but it's going to go up like that. I'm confused about what happens here. Maybe it just gets flat. I'm not sure. But over here, I can see that we're shooting down with a slight curvature this way, and then it seems to stop. Maybe it's going to go up like this. I don't know. We'll see. Let's try it out and see. I tried following those currents, and let's see how well I got it. So I'm just going to match this right here. Yeah, I got a pretty good match there. Looks pretty good. So you just follow the current, and there you go. Let's do another one. What if I were to drop the stick like maybe, right here? Can you trace what that would look like? Following the current, it looks like it kind of shoots down and points to the left. And then it starts to really flatten out here. And then I'm not sure what this is all about. Maybe it does something like that. And then here it just kind of shoots straight up. So let's see how well I matched it. Pretty good, not too bad. I got close. So that's the idea, okay? So we have a slope field, which is all the slopes. But if you imagine it like you're dropping a feather in a current and trace that out, you get the shape of the original graph, the original solution before we found its derivative. In other words, you're getting the shape of a particular solution to this differential equation, okay? And that's the first thing I want you guys to do today is on your student practice worksheet. I would like you guys to go through these 6 graphs, and here's the dot. That dot represents the feather that you're throwing into the river. And I want you guys to do your best to see if you could sketch a particular solution from there. And by the way, why are we calling this a particular solution? Remember, we talked about that, where you have a differential equation, which is an equation with a derivative, and a particular solution is what you get after you integrate it, so it's the original function. But when you do that, you get a c, right? But don't we need an initial condition, a point to plug in, so that we can find the c? Well, guess what? The slope field represents the derivative. The point represents the initial condition. And the line that we're tracing is the graph of the particular solution. So that's why we're using that vocabulary. So we're just doing the geometrical side of the differential equation math that we did way back, I think, in lesson 2.2. But anyway, so for each one of these graphs, you're given a particular solution and a slope field. Your job is to sketch a particular solution by using that analogy of like throwing a feather in a river and following it along. So pause the video here. When you unpause it, I will have the solutions up for you. So once again, we have the slope field, which represents the derivative. We have the point, which represents the initial condition. And the lines that we've drawn here, by using the analogy of a feather floating down a river, the lines that trace out in that slope field through that point give us what's known as a particular solution. Okay? Now, based on that, let's go ahead and move on to the next part of our lesson. So, to do this part of our lesson, we need to review some pre-calculus stuff here for a second. We need to talk about function families and what they look like. Okay? So, we have constant functions. Constant functions are functions where you have y equals a number. Okay? When you have that, the graph just looks like a flat line, and that's it. Then we have linear functions. Linear functions are of the form y equals mx plus b. Technically, a constant function is a linear function. It's just a special one, where it's just a constant, so it looks like a horizontal line. But linear functions are also straight lines, but they can be diagonal, like that. Another type of function is the quadratic function, which I think you guys are probably very familiar with. Quadratic functions are of the form x squared. It could have other stuff, like there could be a number here or another number here or something like that. But the point is that there's an x squared present. And anytime there's just the highest power is an x squared, then you end up with a parabola-looking shape. And remember, it doesn't always have to be going upwards. It could be upside down or something like that. Okay? We looked at a cubic function earlier today. We graphed this one, remember? Cubic functions look something like this. What else could we do? How about square root functions? Square root functions look like half of a parabola tipped over on its side. So square root functions look something like that, like a half a parabola, but just tipped over sideways. So what do I mean by half parabola? Like there's a whole parabola, right? But it's not a whole parabola. It's only half. So it would look like that. Cube root functions that they look a little bit like a square root function too, actually, but they have a tail on them that looks like that. So they basically look like a cube function just flipped over on its side. What other kinds of functions are there out there? How about absolute value functions? Like if you have y equals absolute value of x, those tend to look like a V shape. Now all of these functions could be transformed, so they could be stretched, they could be translated, they could be flipped upside down, they can be flipped sideways. They can all be made to look a little bit more complicated, but these are generally what they look like. What else is there? What other kinds of functions can I share with you guys? Sine functions. Haven't seen those in a while. Oops. Sine functions and cosine functions look pretty similar. So I'm just going to kind of group them together here. They both just look like a wave. The only difference is where the wave starts and stops is a little bit different, but they both look like waves. Whereas tangent and cotangent functions tangent looks a heck of a lot like a cubic function, honestly. Cotangent looks the same, but it's backwards. We could do secants and cosecants, but I don't think I'm going to give you guys anything like that. What else do we need to know? There's just so many different kinds of functions, but the point is that you guys should be able to identify what the function is based on its shape. So if I gave you this, you should be able to tell me, oh, that's a quadratic. That means it has an x squared. Okay, so that's what we're going for here. Oh, I know two more. We have exponential functions. Exponential functions are things where you have any number. I'm just going to use e because that's the one we typically use. But you have any number being raised to the x power. And those have a horizontal asymptote, and then they shoot up really fast, so they look like that. Logarithmic functions, and once again, usually we use ln, so logarithmic functions look a lot like exponential functions, but just kind of oriented a little bit differently. They have a vertical asymptote, and then they shoot sideways, but very slowly. So those are logarithmic functions. So nice little thing to have. I'm going to give you guys a worksheet later on this year with all these on there and a little bit more information about each one of them. But for today, it might be nice just to have it as a reference so that you can do the activity we're going to do. So let me show you what we're going to do with this thing here. So what I've done here on this Geogebra site is I've entered this differential equation. Y prime equals 2x. And here's the slope field that goes with that. So I want to know what would the particular solution look like? What would a particular solution look like? What would the equation be? Well, look at our slope field. And just imagine you drop a dot in here somewhere, like maybe here. Let's trace it to get an idea of what the particular solution might look like. Well, gosh, that looks an awful lot like a parabola. And what do we know about parabolas? Oh, I know. Parabolas are x squareds, right? So I don't know exactly what the equation of that line is, but I do know that it should be a parabola, because based on the shape of the particular solution that I sketched using a dot, I could tell it should be a parabola, which suggests to us that this must be a quadratic of some kind. Now, honestly, we could just do this very easily just by integrating both sides, and sure enough, if we do that, it's exactly what I have over there. But that was really just luck. If I had put it up here, then my solution would look like that, which, in that case would be, a different C value than 0. But anyway, I'm rambling. But you guys got the idea. So the point here is that today, you guys are supposed to be able to match your slope field, not with a differential equation, but with the particular solution. So let's look at your guys' worksheet here. Now, we did all these earlier. Let me put them back up. Now, each one of these graphs up here goes with one of these. Now, observe what we have. You guys have a square root function. So which one of these graphs looks like a square root function? I just showed you guys what they all look like on the last slide. So whichever one you think that is, you're going to fill in your blank. Hopefully you guys know that the square root function is this one. It looks like a half of a sideways parabola, as we said, right? So that means that this slope field goes with this particular solution. So I'm going to fill in my blank down here and put my plus C there, and then I'm going to cross it off because I'm done with it. I would like you guys to go through and match the rest of these with their graphs up above. Once again, you should be able to tell, based on the shape of the particular solution, what kind of a function it is, so that you can pick the correct equation that goes with it. So pause the video here and see if you guys can match them, and then we'll move on from there. And there's your solutions. So the first one, because it has that wavy shape, we know that that has to be some kind of a sine or cosine graph. We have the parabola in the middle, so we know that's a quadratic of x squared. The one on the right seems to get flat as we move to the left, and that would suggest there's a horizontal asymptote, which is an exponential function, which is e to the x. We looked at the cubic one already on the bottom left. We saw that earlier today. And then we have a nice one of those slope fields where the slope is the same everywhere, which would suggest that we have a linear function because it's going to end up being just a straight line. All right, so there you guys have it. So we've accomplished our goal for the day, and that's the end of the lesson. It was a pretty short lesson. Just want to make sure, though, that we revisit what's going on here. So what is a slope field? A slope field is a picture of all the slopes of some given differential equation. And what we learned yesterday was how to sketch these by plugging in points, and we also learned how to match them. And the way you match them is by looking at the slopes and comparing them to the slope equation. If all the columns are the same, if all the horizontal rows are the same, or that means one thing. If the zero slopes match in certain places, that means another. So you're comparing the slopes to the equation. But today we also learned about initial conditions. And we know from way back in lesson 2.2 that when you integrate a differential equation and plug in the initial condition, you can find a particular solution. And that's represented by the picture that we draw when we sketch the line going through the dot. We can match the slope field not only to the differential equation like we did last time, but we can also match it to the particular solution by looking at the shape of the curve that is sketched when we sketch that particular solution. And so that's our summary of slope fields, and that's what we've learned in these past 2 days, and that's all I'm going to be expecting from you guys with regards to slope fields. So that's our last lesson for Unit 2, and from here on out, it's all about testing and then moving on to Unit 3. So see you guys later.